class, so chapter 3 talks about systems of linear equations, whereas before we were working with just one linear equation, now we're going to be working with multiple linear equations. So the first thing we're going to do is talk about systems of linear equations in 2 variables, and then we're going to work our way up to 3. So it's important to note that equations of the form ax plus by equals c are linear equations, right? That's the general form or standard form of a linear equation. And the solution of a linear equation would be the graph of that line, which is every set of ordered pairs along that line. If instead we're given 2 linear equations, we would call that a system of linear equations or a linear system. A solution to a system of linear equations are the ordered pairs, there could be multiple, that satisfy both equations. So there are 3 different types of solutions we can have given a system of linear equations. So firstly, if our lines intersect at a point, we will have exactly one solution, and that is the ordered pair of their intersection. If lines are parallel, because they never intersect, there's no point that would be true for both of these lines, so that would have no solutions. And if for some reason our graph was the exact same line, one on top of the other, that would have infinitely many solutions. And you may remember my interpretive dance from class. Who could forget it? So how do we solve a system of linear equation? Well, there's 3 different ways: graphing, substitution, and elimination. Let's start with graphing. So the first thing we're going to want to do is graph our first equation, graph our second equation, and determine what the solution is and check our solution. So here I have x plus 2y equals 2 and x minus 2y equals 6. I'm going to want to go ahead and get these into y equals mx plus b form. Remember, if I solve for y, m gives us our slope and b gives us our y-intercept. I'm sure we're all really good at this by now, but let's go ahead and subtract x from both sides. I get 2y equals negative x plus 2. I divide both sides by 2. Y equals negative 1/2 x plus 1. Now I do the same for my second equation. I subtract x from both sides. Negative 2y equals negative x plus 6. I divide both sides by negative 2. That means I have y equals 1/2 x minus 3. So here, let's graph this first equation in green. My slope is a negative 1/2, so it's negative. That means it's going to look like it's going downhill. And my y-intercept is 1. So I know slope is rise over run. So since it's negative, I'm going to go down 1 and over 2. Down 1 and over 2. Here's a slope of negative 1/2. And let's go ahead and draw our line as neatly as possible. Okay, not bad, not bad. Next, I'm going to graph my second line in orange. That line is y equals 1/2 x minus 3. This is a positive slope, so my graph's going to look like it's going uphill. And my y-intercept is negative 3. So here's my y-intercept. This time I've got a positive slope, so for every 1 I go up, I go over 2. Up 1 over 2, 1 over 2, right? And we can graph this beautiful line. Remember, you really only need to plot 2 points in order to graph a line, but because we're looking for the intersection, I wanted to graph as many points as possible. And you can see, look, here's where our 2 lines intersect. So our 2 lines intersect when x is 4, y is negative 1. And I would check that by plugging this ordered pair into both of my equations, not just one. So I'd have 4 plus 2 times negative 1 equals 2, which gives me 2 equals 2. I'd have 4 minus 2 times negative 1 equals 6. 4 plus 2 is 6. I agree with that. So this is indeed the solution to our system of linear equations. Let's graph a couple more examples. I have 2x plus 3y equals 4 and 4x plus 6y equals 12. I'm going to go ahead and get both of these into slope-intercept form. I do that by isolating my y variable. If you have any questions about what I'm doing here, I would definitely recommend go back to review some of the chapter 2 videos. All right, let's go ahead and graph these lines. I'm going to graph my first line in blue. I'm sure you can already see there's something interesting about these two lines. They have the same slope. So in blue, we'll graph our first line. That's y equals negative 2/3 x plus 2. So my y-intercept is 2. My slope's negative 2/3, so I go down 2 over 3, down 2 over 3. And here's my beautiful line right here. Let's look at our next line. We're going to graph that in green. My y-intercept is 4/3, which is a little bit more than 1, right? So I go down 2 over 3, down 2 over 3, and I can graph my line. And because these lines have the same slope, this is going to have no solutions. Okay, so you can draw the symbol for the empty set, or you can write no solutions because these two lines are parallel. All right, one more time, we're going to isolate our y variable. I'm going to add 4x to both sides. I have 2y equals 4x minus 3. I divide both sides by 2. I get y equals 2x minus 3. Look, both of these are the exact same line. My slope is 2. My y-intercept is negative 3. 1 over 2, up 2 over 1, right? This is our slope because it's rise over run. 2 over 1, right? So both of these are going to be the exact same line, and that means that there are infinitely many solutions. Now, I don't want you to write from negative infinity to positive infinity. What I want you to write is infinitely many solutions, because both of these lines are the same. So when we're graphing solutions and finding solutions to systems of linear equations in two variables, okay? If the system has a solution, we say it's consistent. And if the two equations are different, so they graph at intersect at a single point, we call those independent. If two graphs are parallel lines, remember that means there's no solution, so instead of consistent, we would call that inconsistent. But because these equations are not the same, they're still independent of each other. And if the graph is, two graphs are the same line, we say that's consistent because there's a solution, but the equations are the same, so they depend on each other.